Let's talk about nuclear chemistry. All right, so what is a nucleon? A nucleon is quite simply a particle in the nucleus. So that includes protons, which have a positive charge, and neutrons, which have no charge. Atomic notation should look familiar, remembering the top number represents mass number, bottom number represents atomic number or charge, and those are located on the left side of the symbol for the element. And remember that mass number is protons plus neutrons, and atomic number is simply the number of protons. So if we want to find the number of neutrons, we would subtract those two numbers. So some examples, how many neutrons are in this nuclide? So that's oxygen. 18 is the top number. Why? Because they don't have to tell you the atomic number, because where can you look? Bam, periodic table. So that's 8. So I would do that subtraction to find the number of neutrons. Now the next one, how many protons are in this nuclide? Well, protons is the same as atomic number. So bam, you look it up on the periodic table, and how many protons does it have? And you write your answer right here. Now, the next one, what is the mass number of a nuclide with 13 protons and 12 neutrons? Remember, that mass number is the number of protons plus the number of neutrons. So if I know how many protons and I know how many neutrons, what do you think I do? Yep, I add them together, and that gives me the answer that goes here. Now, just as an aside, that element is going to be here. Why? Because look, it has this many protons. And then what is the atomic number of a nuclide with 13 protons and 12 neutrons? So the same nuclide. And again, atomic number is the same as what? The number of protons. So you should have answers for all of those. Now, what are isotopes? Isotopes have the same atomic number, but different mass numbers. So that means they are the same element, so they have the same number of protons, but a different number of neutrons. So the same atomic number, different mass number, same element, same number of protons, different number of neutrons. Now, not all nuclei and not all isotopes are stable. It really depends on the ratio of protons to neutrons. You can see this line right here follows a 1-to-1 ratio. So you can see for elements that are small, right, it's basically a 1-to-1 ratio that enables the isotope, that particular nuclide, to be stable. But as we add more and more protons, we have to add more neutrons for it to be stable. So for example, if I look at something that has 40 protons in its nucleus and go up here, it needs around 50 neutrons in order to be stable. Then if I go to 70 protons and go up, it's going to need somewhere around 100 neutrons to be stable. So this whole band is called the band of stability. And it literally shows all of the nuclei that exist. Those ones that are blue are stable, not radioactive. And all the green ones are radioactive. Now, just as an aside, if you look on the periodic table, you'll see some atomic masses listed in parentheses. That means they have zero stable nuclei. They're all radioactive. So what happens when an atom is unstable? Well, it will decay according to its half-life, and the nucleus is simply going to break apart. The nucleus will continue to break apart until it is stable. So radioactive decay will eventually produce a stable nucleus, and will keep going through the process until it is stable. Now, this could occur in one step, in this case showing an example with carbon-14. In one step, it becomes a stable nucleus. But uranium-238, for example, that stability occurs in many, many steps until finally we get to lead-206 at the end of this chain, and it is stable. So what happens in nuclear reactions? So what happens when a nucleus decays? Some important concepts here. First, a little bit of mass is converted to energy. So that means huge amounts of energy are produced. So in a nuclear reaction, I don't care what kind of a nuclear reaction, in any nuclear reaction, it will always produce more energy than any other type of reaction. So more than all of the organic reactions, polymerization, saponification, fermentation, etc., more than single replacement, more than synthesis, more than combustion, more than decomposition, more than all of them. Always the reaction that produces the most amount of energy is going to be nuclear. And it's a huge amount of energy that's produced. And it may release some radioactive particles. So that's a downside, but we'll talk about that later. So I hinted that there were many types of nuclear reactions, but all of them converted mass into energy. Teeny tiny little bit of mass, but that's enough for it to be a huge amount of energy. So what are the kinds? Well, first we have transmutation reactions. So a mutation is a change, right? That word should sound familiar. Trans means to change into something else. So in a transmutation, one element changes into a different element or a different isotope. And typically that means the number of protons changes, so the element changes. So we get a new element. Now, there are two types of transmutations. We have natural and artificial, and they can be called either natural transmutation or natural decay, and artificial transmutation or artificial decay. So for natural, it just happens. I don't have to do anything. It just happens. But if it's artificial, I have to force it. And how do I force it? I punch it. Well, I don't really punch it, but I could force somebody to fight by punching them. But an artificial transmutation, you hit it with a particle, and that causes the nucleus to decay. So here's an example of a natural transmutation. How can you tell it's natural? You look on the reactant side and you will see one thing. That means the thing was just sitting there and decayed. I didn't have to do anything. I didn't have to force it. It just happened. Okay, that's how I tell it's natural. There's one reactant. Now, if it's artificial, okay, I'm going to see two reactants. So that means I needed to bonk this aluminum with, this is an alpha particle, in order to get it to react. I needed to bonk this lithium with an alpha particle. Sometimes you hit it with a neutron, often with an alpha particle. But whatever the reason, I had to hit it with something else in order to get it to decay. So it's artificial. Now we also have fusion and fission. Okay, now those two terms look similar, so they tend to be confused. So let's go over it. So fusion is when two small nuclei form one larger nuclei. Fission, on the other hand, is when we take a big nucleus, bonk it, usually with a neutron, and split it apart into smaller nuclei. So that often occurs in nuclear power plants. Whereas fusion occurs in stars, like our sun. So here's a fusion over here. Two little nuclei combine and form a larger nucleus. And over here, we have fission, where we have a large nucleus, usually bonked with a neutron, and the nucleus splits apart and makes smaller nuclei. Now, which reference tables will we use to help us through this process? Well, one is table O. We've looked at this before. And just as a reminder, mass numbers are located on the top, and a charge, or the number of protons, if it's at least one, is found at the bottom number. Remembering that beta particle is the same as an electron. Okay. We will also use table N. Table N talks about decay modes, and that's when we're going to kind of slip into. Now you can see that it is the nuclide name, and here's the nuclide. So nuclide just literally means a specific nucleus. So we could say gold 198 like this, or we could say gold 198 like this. Why don't we put the atomic number? Because we could just look it up on the periodic table, right? Now, all the nuclides in table N decay spontaneously. That means they're natural transmutation. Don't have to bonk them. They're natural decay. They just decay on their own. So let's look at those types of decay modes on table N. One is alpha decay. So what does alpha decay mean? Alpha decay means that it produces an alpha particle. So here's an example where we have alpha decay. Okay, so we have a nucleus and it decays spontaneously and produces a new nucleus and an alpha particle. We also have beta decay. So here are examples of beta decay, right? Has a lot of them. Here's two. Okay, so in this case, a beta particle is released and then a new nucleus is produced. We can also have positron decay. So here's an example of positron decay. So in positron decay, positron is released and we get a new nucleus. Now, not listed on table N, but gamma decay is possible. In this case, I get gamma radiation released, okay? So gamma radiation is released. Now, it's also important to understand that between alpha, beta, and gamma particles in particular, which way they will be deflected in a magnetic field or in an electrical field. So this is a reminder that if we had a beam of particles, the electrons would be attracted toward the positive pole, the positive magnetic field or the positive electrical field. Protons would be attracted toward the negative, and neutrons would not be attracted or not be deflected at all. They would pass through undeflected. Similarly, if we look at the particles in table O and we look at the charge at the bottom, that's going to determine whether or not it will be deflected by a magnetic field or an electrical field. So beta particles, because those are electrons, are attracted toward the positive. Alpha particles or helium nuclei are attracted toward the negative. Gamma particles, just like neutrons, will pass through undeflected. So not only the deflection, we also have to understand the penetrating power. And for this case, I'm going to look at the top number and the bottom number and how big those numbers are. So if I held up a piece of paper, alpha particles would get stopped. Why? Because they have a lot of mass. So they can't get through. But beta particles and positrons and gamma can get through that paper. Okay. Then if I held up a sheet of aluminum foil, well, the alpha particles were already stopped by the paper. And now we have the beta particles and positrons that are going to get stopped by this aluminum foil. But the gamma radiation can continue through because it not only doesn't have mass, but it doesn't have charge, okay? Then we get to concrete, and gamma can partially get through concrete or thick slabs of lead, but that's going to provide the best protection against gamma. So in terms of which ones can penetrate through stuff, gamma has the most penetrating power, and alpha has the least, and then beta, positrons, is going to be in the middle. Then if we talk about ionizing power, that means the ability to hit something and cause it to lose electrons. So this is going to be the flip side. So whereas alpha particles are stopped by a piece of paper, but when they hit something, they're going to hit with more mass, so they can cause electrons to lose. Okay, so alpha particles have the most ionizing power because they have the most mass. Gamma particles have the least ionizing power. Okay, so in terms of penetrating power and ionizing power, it's flip-flopped. Now, nuclear reactions have both benefits and risks. So certain radioisotopes or radioactive isotopes, like the ones in table N, have specific uses. So this is a benefit. You need to know these because you kind of have to remember them, all right? So carbon-14 is used to date organic material, things that had carbon in it. So things that were once living, like trees or people or animals, skeletons. Okay, what do we look for? How much carbon-14 is left. And over time, the carbon-14 naturally decays. So as things are older, there's going to be less of the carbon-14. Iodine 131 is used for your thyroid. So it's used to diagnose and treat thyroid disorders. Iodine, thyroid. Cobalt 60 for cancer treatment. Now, you don't necessarily have to remember that it's cancer treatment, just that it has to do with cancer. Uranium 238, that's for dating rocks and minerals. Why? Because they have been around a lot longer, and uranium has a really long half-life. And then technetium 99, and this is used for cancer detection. So if you remember, carbon 14, iodine 131, and uranium 238, the remaining ones, cobalt 60 and technetium 99, are both related to cancer. Well, what are some other benefits? Well, nuclear reactions, remember, produce way more energy than any other kind of reaction. Nuclear energy is actually pretty reliable. So once we get a nuclear power plant up and running, it can run with very little interruption or maintenance. And its cost is low if we compare it to natural gas or coal, and has no impact on greenhouse gases. So it sounds fantastic, right? Well, what are the risks or the costs? Nuclear plants are inexpensive to run, but super expensive to build. And in addition, they have to use a lot of water to cool their reactors, and this can actually create issues if that warm water is released in the environment, because it affects the organisms that can survive. And some nuclear reactions produce radioactive waste. So what are we going to do with the radioactive waste? In addition, exposure to radiation can be harmful to humans and the environment. It causes changes in DNA. And there are risks of accidents. So accidents or meltdowns in a nuclear power plant can have catastrophic effects on the surrounding area. All right, let's talk about balancing nuclear reactions. All right, so here's the first question. Use the decay mode to write the nuclear equation. So I have a snippet from table N. Here's table O. Here's hydrogen from the periodic table. So you can see that hydrogen 3 decays with B negative. B negative stands for beta particle. Okay, so what I'm going to do first, from the periodic table, I know hydrogen's atomic number, right? And then it's going to go through this natural beta decay, and it's going to release a beta particle. And a beta particle looks like this. And then it's going to change into a new nucleus. What nucleus? Well, let's find out. How do we figure it out? Well, this is my blank. Okay, so I'm going to look at all the numbers across the top. And wherever my arrow is, that's going to be like my equal sign. So on this side, 3 equals 0 plus whatever was here, x. This should be obvious, right? So x is going to be 3, right? Now for the bottom numbers, same thing. 1 equals -1 plus x. Here's where you have to be careful, right? I want x by itself, so I need to add 1 to both sides. So this bottom number is 2. So I have the top number, bottom number, then I need a symbol, okay? So where do I get that? Well, I look at the periodic table and I look for the element that has 2 as the atomic number. Now remember, this is a natural transmutation because it is one reactant, and this is what happens in beta decay. Beta decay has a negative down here, so we have to be careful, right? Okay, now let's try another one. So write the nuclear equation for the decay of iron 53. So I already have included here the atomic number from iron, but we could get that from the periodic table. It is going to release a positron. So here's the symbol for positron. So I know I have this 0 plus 1 and then something else, right? But I'm not sure what. Okay, so remember, wherever the arrow is, that's going to be my equal sign. Let's figure out what belongs on the top. Well, 53 on this side, 0 plus X on this side. Should be obvious, the top number is 53. So let's look at the bottom. 26 equals positive 1 plus X. How do I solve for X? Subtract 1 from both sides, and that gives me 25. So I have top number, bottom number, beautiful. I need a symbol. How do I figure it out? I go to the periodic table and I look up the atomic number 25. In that case, it's Mn. Again, one reactant, natural transmutation. All right, let's look at this one. So francium 220. And again, I have the atomic number here, but I don't have to I can look it up, right, on the periodic table. So this is going to decay using alpha decay, which means it's going to look like this. So a 4, 2, He. That's what I know it releases, and then something else. So let's look at the top. Remember, wherever the arrow is, that's the divider. So 220 equals 4 plus X. So subtract 4 from both sides, right? And I will get 216. Right, now let's do the bottom. 87 equals 2 plus X. I subtract 2 from both sides, and I get 85. Okay, now in order to figure out what element, I need to look up 85 as the atomic number on the periodic table, and there we go. Again, it's a natural transmutation or natural decay because it's one reactant. All right, sometimes you have something like this where you just have to fill in the blank. So you didn't need to know that this was beta decay. They gave you it. So you just have to figure out what goes on the top, the bottom, and the symbol. So again, divide the two sides. So 32 equals 0 plus X. And for the bottom, it will be 15 equals -1 plus X. Up here, that should be obvious. That's 32. For the bottom, I have to add 1, remember, to both sides. And now you need to look up that symbol. What element has the atomic number of 16? All right, now this one can be a little bit tricky, so let me show you what I mean. First, it's a little bit longer. This I can tell is artificial transmutation, right? How do I know it's artificial? I have two reactants because here's my divider and I have two things over here. So, and also you see this note that says, be careful, see the coefficient. So let me show you what I mean. So I have 241 as the top plus 4 equals, right, 2x. So 2 times whatever is here, because that's what that coefficient means, plus 243. Okay, and then for the bottom, I get 95 plus 2 equals 2x again plus 97. Okay, so let's look at the top. So that gives me 245 equals, right, 2x plus 243. And then for the bottom, I get 97 equals 2x plus 97. Okay, so let's do the top one first. I'm going to subtract 243 from both sides, right? And I'm going to get 2 equals 2x, right? Divide by 2. X equals 1. So the top number is 1, right? What about the bottom number? So minus 97 minus 97, 0 equals 2x divided by 2, x equals 0. Now, I can't look up an atomic number of 0, so where would I look this up? On table O. So what symbol would go there? All right, our last topic, half-life. So what is half-life? Well, half-life is the amount of time it takes for a radioactive isotope to decay. So half-life uses time units, like seconds, like hours, like years, whatever. Has to be a time unit. So here's something important to show of what happens in half-life. When something decays, it doesn't disappear. It changes into something else. So the thing it starts with is the parent isotope, and then it changes into the daughter isotope. So it doesn't disappear. But you can see that over time, we have more and more daughter isotopes present and less parent isotopes present. All right, here's another visual to show you. So at 0 days at the beginning, we have all parent isotope. And then over time, we get more and more daughter isotope. And so what half-life means is the half-life of this is 14 days. So at the 14-day mark, half of the parent isotope is decayed. It doesn't mean that at 14 days, bam, half decays. No, it's been decaying all along. But by the time we get to the half-life, half is left. And after another half-life, half of that half. And after another half-life, half of that half of that half. Okay. So again, here is another visual just to show you that over time we get more and more of the daughter isotope and less of the parent isotope. Nothing is disappearing. Now, radioisotopes with shorter half-lives decay faster. So you can see this one on the top is going to decay much faster, whereas the bottom one with a slower half-life takes longer to decay. So this plays a role in what we choose in medicine. So this is important for the usefulness of radioisotopes. So iodine 131 has a shorter half-life, so it's good for diagnosing things in humans because there's less exposure to radiation over time. Carbon 14, thousands of years, that's good for dating things that used to be alive, but uranium 235 or uranium 238 has a much longer half-life, so that's important for dating rocks. But I wouldn't want to use that in a person. Why? Because the whole time the person is alive, it has not even reached one half-life yet. So it would be more dangerous. I would be exposed to more radiation. So remember table N, it shows specific half-lives of different nuclides, okay? So here's an example using cesium-137. So you can see when we start, this is how much we have. So the fraction is one whole. Okay. After one half-life, we have half of the mass, half fraction, 50% as a percent, and the amount of time it takes. Okay. After the second half-life, we have half of this one left, half of this one, half of this one, and it took a whole nother half-life. So 30.2 plus 30.2. And then at the next half-life, right, half of this, half of this, half of this, and a whole nother half-life, so a whole nother 30.2 years. Okay, hopefully it'll make more sense when we do some examples. Okay. How long does it take for a 20-gram sample of calcium-37 to decay to 2.5 grams? Well, let's start. We're starting with 20 grams. When it goes through one half-life, so that's one half-life, I get 10 grams, right? When it goes through another half-life, right? So that's one half-life, I get to 5 grams. And then when it goes through another half-life, so that's a half-life, I am at 2.5 grams. What if I was talking about fractions? Well, I would have one, the whole thing, then half, and then for this one, I need half of a half. So that means half times a half. So that's 1/4. And then next I would have half of a fourth, which is an eighth. What about if I talked about it as percents? I'd have 100%, then it would be 50%, then it would be 25%, and then it would be 12.5%. Okay. Now, the question is asking me how long does this take? So this is just an overview of how we use half-life. But the time I got to get from the reference table, table N, right? And it says that the half-life of calcium-37 is 182 milliseconds. So that means this half-life took 182 milliseconds. This half-life took 182 milliseconds. And this half-life took 182 milliseconds. So how much time did it take all together to get there? Well, I could either do 182 plus 182 plus 182, 182 times 3, okay? Now, what fraction of nitrogen-16 remains after 28.52 seconds have passed? So again, this I don't have a starting mass, so let's just start with 1, right? I have the whole thing. 1 half-life, I'm going to have a half, right? So 1 half-life, I have half left. After another half-life, I have a quarter left, right? After another half-life, I have an eighth left. Since it's asking me to find fractions, this is useful, right? After another half-life, I'd have a 16th. After another half-life, I'd have a 32nd. Now, rarely do you ever have to go past that, so that's why I stopped there, okay? But now I need some information about nitrogen. And nitrogen-16 has a half-life of 7.13 seconds. So that means this half-life from 1 to 1/2 took 7.13 seconds. The next half-life took 7.13 seconds. This next half-life took 7.13 seconds. So did this one. And so did this one. Okay. So I need to, though, find 28.52 seconds. So add these two up. What do I get? 14.26 seconds. Was that long enough? Nope. Add another half-life in. So 7.13. And I'm going to get 939.1. 2139, is that long enough? No. So then try adding this next 7.13, and you will find you get this number. So that means what fraction is left. If I went through this half-life, and I went through this half-life, and I went through this half-life, and I went through this half-life, what fraction is left? Okay. All right, a 500-gram sample of phosphorus-32 begins to decay. What is the mass of phosphorus-32 when 1/8 of the sample remains undecayed? So let's just set the fractions up, right? 1 whole thing, 1/2, 1/4, 1/8. All right, so I know I need to get to 1/8, right? That's kind of messy for. All right, now I know which mass I started with, right? I started with 500 grams. So after 1 half-life, that would be 250 grams, right? After another half-life, that would be 125 grams, right? After another half-life, keep dividing it by 2, I'd get 62.5, right? So what is the mass of the sample when it's 1/8 left? This, 62.5, okay? You can look up how long that would take. That's not the question, but if you needed to know, this one takes 14.28 days. So does this one, so does this one. So it would be 14.28 days times 3 half-lives, right? If I wanted to know how long it took, okay?